have your laptop, like if this goes wrong, you can yeah.
Alright, let's start. I guess we are a little late today, but it's fine. Okay, so a couple of quick announcements. So hopefully all of you have noticed that homework 5 is out. So this is mainly a homework about linear programming and the basics. So if this is a topic that you felt was a little more advanced, then you should probably start homework early. So that's what it is. Another thing that people have asked is whether there will be a next homework, and there will be homework 6, but it's optional because I will be taking the best 5 out of 6 in the end. Yeah.
How many grades will we get?
Yeah, so it's 3 out. Grades.
3 is not out yet.
I mean, twice more.
Maybe this week.
Okay, so
Amazing.
okay. Alright, so homework 3 grades will be out this week for sure. Okay, and 4 will start soon after. The split for these things is done. It's just that I guess TAs are also often busy at this time of the year. So. Okay, so hopefully they'll be out soon. Okay. And so four of them will be out before this stuff. Okay, so yeah. So in fact, homework 6 will be posted early next week. Okay, so this is just so that you have some chance to look at the things and so on. Okay, so it will also be somewhat of a review. So it won't just be the new stuff we've been covering. It will be more of a review of various things in the course. So yeah, that's homework 6. The other thing is that the project midway report, or like the formal proposal, is due this Friday. It's okay if you submit by the weekend. So this is an informal. I mean, this is like a halfway thing. So the only reason I would like you guys to submit on Friday is because I can read some of them over the weekend. Okay, so yeah. So in that sense, it's nice if you submit by Friday, but it's okay to submit by weekend. Yeah.
Do you want us to just ignore it like last time?
Oh, no. So I will create an assignment on Canvas. Okay, so yeah, let's submit on Canvas. And as usual, yeah, so as we will also do for the final project, only one submission per week. Alright, so you can submit more, but it won't be great. So yeah, so that's quick announcement. So any questions on this? Okay, so the last couple of weeks we've been looking at linear programming, and these are just you have some combinatorial problem. You write it as you define some variables, and you write a bunch of equations that these variables must satisfy. And the hope is that solving this optimization problem that gives you the optimal solution you want for this combinatorial problem. So this has been the general theme. And last week in particular, we started looking more in depth at linear programs, which are basically optimization problems where you have continuous variables, which we call x1, x2 up to xn. We often denote it by just one vector x. Okay. And these are linear programs of the kind. I mean, these are just optimization problems of the kind you want to minimize some C transpose X subject to a bunch of linear constraints. So this is the general form of a linear program. And we said that last time we basically saw the details of the simplex algorithm. And the reason we saw it is because I wanted you guys to get a sense of the geometry of how the set of feasible solutions to this looks like. One thing we argued is that if you look at the set of all feasible solutions, it's called a polytope. It could be bounded or it could be unbounded. And it's defined by a set of these planes. We said that the optimum value is always attained at a corner point. Okay. And then we spoke a little bit about what are corner points. Okay, so we saw two views of this. So the first view was that a corner point is an intersection of n of these inequalities where you view them as equalities. Okay, so these are like the planes, and this was again driven by the 2D infusion. And and we also saw how you get neighboring corners. And then we saw the simplex algorithm, which was essentially moving from corner to corner so that you always update the objective function. You always improve the objective. Okay. And then we saw an alternate definition of corner point last class, which was kind of nice. So it said that if these are points where no matter what direction you move, okay, so these are points P, such that no matter what directions you move, at most one of P plus Z and P minus Z is inside the polygon. Okay, so this is what we saw. Okay, so let me not rewrite it because this is what we saw last time. Okay, so at most, so in an example like this, if you are here, there are directions where moving a little bit along both these axes will keep you feasible. Okay, so that means that this point is not an interior. This point is not a corner point. But for the corner point, there is no direction for which this and this are both within the point. Okay, so this is what we see. And one of the other nice things we saw is that you can write linear programs for combinatorial problems, okay, like matching and so forth. And in some cases, you get lucky. Okay, so we said that when you write a linear program that captures matching, it turns out that all the corner points of the feasible region are actually 0-1 solutions, okay, which means they correspond to actual matchings. Okay, so this is why you can optimize over this continuous space, and you can still do that. Okay, you can still find the optimal matching. As somebody pointed out, this can be used for solving weighted matchings and so on. In fact, this is the only algorithm we have seen so far in this course for weighted matching that actually computes the exact outcome. So we saw local cells that gets factor of 2, factor 2/3, stuff like this, but this is the only solution that gets exact. All right, so this is a little bit about matching. And well, in general, I said that there are two ways people argue about corners being integral. So one is we are using argument based on determinants, and I sketched it very, very vaguely for the case of matchings, and I also said that this is often tricky. Okay, so usually this, going by this characterization of the corners, like trying to show that there's always a direction which you can perturb, this is usually the best way to prove that all corners are. All right, so this is roughly what we used to see. And then we started looking at this other problem, okay, which is called vertex cover, and we motivated it by like you have a graph, an undirected graph, like we said edges correspond to roads or something, and we want a policeman at some intersection so that they monitor every possible road. So this is what we asked. So formally the problem is you want to find a small set of nodes S such that every edge has at least one of its endpoints. So, okay, so I shouldn't say neighbors, I guess I should say endpoints. Okay, so every edge has at least one of its endpoints chosen. We said that there's a natural way to write this as an optimization problem. And we said that the variables have to be xi, where I corresponds to the vertices, because you want to select a subset of the vertices. And ideally you want them to be 0, 1, but we are in the realm of linear programming, so you just say that they have to be in the interval 0, 1. So this is what we said. And we said that for every edge, at least one of its endpoints, for any edge ij, either xi or xj must be picked, okay, which means that xi plus xj must be at least 1. Okay. And your goal is to minimize this xi. So one thing you can observe is that if you happen to get a 0, 1 solution to this is a valid solution to the problem you want to solve. So somebody was asking, what does it mean to give a so one of the homework problems asks you to show that this linear problem, this optimization problem captures the problem that you want to solve. Okay, and people are asking, what does it mean for an optimization problem to capture the combinatorial problem you want to solve? Right? So I mean just this, right? So you want to argue that if you can solve this program and if you happen to get 0, 1 solutions, does this actually translate to a solution to the original problem? Okay, and in this case it's quite clear because a 0, 1 solution just means it's an assignment of zeros and ones, okay, which basically means you're picking a subset of the vertices. Okay, the ones correspond to a subset of the vertices, and if it satisfies all the constraints, then for every edge you're picking at least one. So that's all I mean when I say that try to argue that this captures. Alright, so that's this, and we want to minimize the sum of xi. Yeah, and last time we said that in this case you can actually come up with, in some sense, a cheating solution. Okay, like when you are looking at this continuous optimization problem, a solution that puts xi equals half for all the vertices. So if these are vertices A, B, and C, so you have xa equals xb equals xc equals half. So this solution satisfies all the edge constraints because sum of any 2 is bigger than equal to 1. But this gives a sum of xi in this case. So this value is equal to 3 by 2. But of course, there cannot be an actual solution whose cost is 3 by 2 because you have to pick at least 2 of the endpoints if you want to watch every edge. So this shows that sometimes the value of the LP can actually be strictly smaller than the real optimum value. So one thing to note is that the value of the LP, the optimum value of the LP cannot be larger than the true optimum value. So why is that? This is an easy fact, but it's something you should remember. Yeah.
Wouldn't the solution be in there? So you chose the solution, it's not going to be higher than itself.
Yeah, so basically you can actually choose a real solution, which is a 0-1 assignment, and that would obviously satisfy all these constraints. Okay, and that is a feasible solution, and so your minimization problem will, if anything, find something that's better than that. Okay, and so this is an obvious fact, but it's just something you should know. That, Because you take any the solution, any valid solution to the problem, it's also feasible for this LP, because that's how we wrote the constraints. So the actual minimizer cannot be small. And this is an example where the actual minimizer can actually be strictly smaller than any optimal. Alright, so I want to claim that in this case, okay, the optimum solution could be smaller. Of this LP could be smaller, but it can't be too much smaller than the true integer. So the theorem is the following. Okay, so if we denote by if opt LP denotes the of the linear program, and opt, I will just call it opt sub VC. VC is the problem, vertex cover. Okay. And opt VC denotes the optimum 0, 1 solution. The value then I want to say that opt LP is bigger than or equal to half of opt VC. Okay. And I just argued that opt VC is bigger than or equal to opt. So we said that the optimum solution for this linear program can only be smaller, okay, which means that the true optimum is bigger than or equal to opt LP. But I also wanted to say that opt LP cannot be too small, so it's at least half of the true optimum. And yeah, you can write it in this different ways. If you like it, you may also view it as saying that you could also write this as opt VC is less than or equal to twice. It depends on how you like to think about it. Alright, so this is what I want to claim. Okay, that the optimum to this continuous problem is smaller than the true optimum, but it's not too much small. And the way we show such things is what is called rounding. Okay, it's by a technique called rounding. And the idea is you take any solution to this continuous problem and you round it to a 0, 1 solution. Okay, and it could be the rounding could be done in any way. I just mean convert as a fractional solution to a 0, 1 solution. So that process is called rounding. So the do is by rounding a fractional solution x to an integer. Let me write the 0, 1 solution. And so what we do is we give a simple way to convert a fraction solution xi to an integer solution. We will call it, let's say, yi, so that the costs are not too different. Okay? So that the objective values are not too different. So 0, 1 solution, so that the objective values are not true. so this will be our goal. Right? So let's see how to do this. So we are saying that start with any some fractional solution xi, I going from 1 through n, where n is the number of vertices, and come up with yi, which belongs to 0, 1. So this is what we want to do. And then we know that the x's also satisfy all the constraints. Okay, so x's, these satisfy 0 less than equal to xi less than equal to 1, and xi plus xj will be 1 for all x's. So this is one example where an obvious rounding works. Okay, so what would be an obvious way to convert fractional numbers between 0 and 1 to actually 0 and 1? What does that mean?
Dividing by the sum square of sum.
How does that happen? If you were just to round a bunch of numbers, how would you do it? Sorry?
It's rounded normally, 0.5 rounds up to 1. Anything below 0.5 goes down to 0.
Yeah, so in this case, you can try doing the obvious rounding, right? Like anything less than a half, round it to 0. Anything more than or equal to half, round it to 1. Okay. Worthwhile trying, right? Like you want to come up with a simplification. So you could say, if xi less than 0.5, set yi equals 0. If xi bigger than or equal to 0.5, so this is a very clean rounding. You can just do it for every vertex separately. You have a question?
I assume, are you going to show it doesn't work? Or an example where?
Do you think this doesn't work?
Yeah, an example where that doesn't work.
Okay. So what do you mean? Firstly, what do we mean by that doesn't work?
Where if you follow this rounding scheme, you will have violated your inequality that you set up.
Okay. So why would that be? So what he's saying is, if these things are satisfied, and he's trying to argue that these things may not be satisfied. So why is that?
Actually, no, I realize my current example is wrong.
Yeah.
Yes, this one has
Yeah, so in this case, this actually is true, right? Because if xi plus xj is more than 1, it can't be that both of them are less than a half, right? So at least one of them has to be at least half, in which case that corresponding y would have gotten rounded up to 1. Okay. So this is a very clean solution, right? So it says that if xi plus xj is at least 1, then so if the x was a feasible solution, so is the y. So this is great. So we started off with a feasible fractional solution. We came up with a feasible integer solution, 0, 1 solution. Okay. So this is fine so far as satisfying the constraints goal. So now the question is, what happens to the objective? Okay. Because that's the more important thing, right? Because you can always say, I come up with an integer solution where everybody that's not 0 is rounded up to 1. Okay, so that would satisfy the constraints also. But the question is, what happens to the objective value? Okay, so the objective we call is sum over I xi. So I going from 1 to n. Okay, so can you relate this quantity? Can we relate this quantity and sum over I going from 1 to n of y? So is the question clear? So this is the objective value for this fractional solution. And after you've rounded it, this is the objective value. You want to say that this value is not too much smaller than this value. This is not too much smaller than that. So how would you be able to say this? And remember, I'm shooting for a multiplicative approximation. Right? So I want to say that this value is, say, at least half that. Yeah.
Each y equals 2 xi. That's less than 5 worst case, xi.
Excellent. Yeah. So what he's saying is that you can actually analyze this for each I. Right? So for every I, okay, so yi is at most 2 times xi. Because if xi happened to be something like 0.2 or something, then yi is actually 0, which is even less than xi. Or in the worst case, xi could be exactly half, okay? And then yi would be 1. But even then, yi is at most 2 times xi. So for every I, this rounding procedure satisfies the inequality that yi is at most 2 times xi. Sometimes it could even be better, right? But in the worst case, this is true. And this means that the sum over all I yi is less than or equal to 2 times sum over I x. And what does this mean? So this means that opt of the vertex cover is less than or equal to 2 times opt of your linear. Because you could have started with the best solution x to your linear program, whose value is equal to opt of LP. And I have exhibited a solution y such that whose cost is at most 2 times that. And therefore the optimum solution, integer solution to the original problem will be at most. So this is what we have shown, and note that this is exactly what we wanted to show. Right? So we wanted to show that opt LP is at least this, or I said this is equivalent to this. Okay? So this very simple proof shows that you can get from any fraction solution to an integer solution with a factor 2 loss. And this means that this linear program, it might have a value that is strictly smaller, but it won't have a value that is much too small compared to the optimum. So it will be at least half. And also note that this gave you a new algorithm, right? So what it said is you wanted to solve this discrete optimization problem. And now you came up with a linear program, which is a continuous optimization problem. We know that there are for solving any linear program. So let's say you used one of them, and you ended up with a corner point x. Now this corner point could have fractional values. And what we said is you do the natural rounding, where you round up any fractional value more than a half to 1. Fractional value is less than a half to 0. You end up with a solution y. And we've proved that the solution you got has a cost that is at most 2 times the. Okay. So this, as we saw, so these kind of algorithms are called approximation algorithms, right? So where there is, so what we have shown, what we proved is there exists an efficient, by this we mean polynomial time, algorithm that produces a solution yi whose cost is less than equal to 2 times the option. Okay. So in fact, what we have produced is at most 2 times opt of LP, and we know that opt of LP is only smaller than 2 times opt of P. So this is just to be clear. Alright. So this is, so note that this is not like any approximation algorithm we've seen before, right? Usually we saw like some greedy algorithms, or we saw some heuristic about which you could argue that you get you have some approximation guarantee. Right? So this is quite different. What we said is you start off with an optimization formulation, a discrete formulation. You make it a continuous formulation. This is something that you can solve efficiently, okay? And then you round the solution to get an. So this is a very popular paradigm. So this works for a lot of approximation problems, and this is often called the relax and round paradigm. Okay. And what does it mean to relax? So this is the process of writing a discrete opt and moving to a continuous optimization. And rounding is basically what we saw before. It's just converting a fractional solution to an integer. Okay, so this is a very popular framework for approximation algorithms, and this is used all the time in a lot of applications. Okay, so and very often in applications, you relax, and many variables will turn out to be integers. There will be a few that are probably not integers, and those guys you have to round. Okay, so that's what often happens in practice. So this is used a lot in problems where you have no idea how to get an approximation algorithm, and you don't. But maybe writing it down an optimization formulation is probably easy. Right? So as we saw for many problems, just writing down some optimization formulation is not that difficult. And you then relax it to something you can solve, and you hope for the best. So that's so this is called relaxing round paradigm. And in fact, so people have recently observed that for some optimization problems, like in practice, for the kind of instances that you get, you don't even need to round. Okay, so most of the variables will already be integer. Okay, so there are all these nice properties that people. All right, so this is one example, and I wanted to mention one bad example for this, okay, which kind of illustrates that this doesn't work for all problems. So I wanted to show two extremes, and then I will go to a problem that's kind of in between. Okay, so this is the other extreme. Okay, so here, so this is called the independent set problem. I think we have seen this before, but we have never really. Yeah, so we haven't really seen algorithms for this because there are no good algorithms for this. Okay, so this is a problem where you're given some undirected graph and you want to find the largest possible set of nodes that don't have any edges. Okay? So it's like saying you have a bunch of people, some pairs of them don't get along well. You want to find the largest group so that everybody gets along as a group. Okay, so that's one of the ways of looking at this problem. So it's and you have a bunch of edges. And people also use this for like coarse conflicts and stuff, right? Like you have you put an edge between two like courses are vertices. Put an edge between two of them if they conflict in terms of timing or something. And let's say you have some enthusiastic person who wants to take as many courses as possible. So this would be, I see one. Yeah, so they would, so you would want to pick the maximum number so that you don't have any edges. So that's this problem. So it turns out that this is a very difficult problem to solve. In fact, there is no known polytime algorithm that has an approximation ratio even something like n to the 0.99. Okay, so this is not that this is a ridiculous approximation ratio, right? So it's like saying if the approximation ratio is n, then that's like saying that if the optimum is the whole thing, then I give you one vertex. If the approximation ratio is n to the 0.99, it's like saying that I tell you that the optimal solution is like n to the 0.99. I just want you to give me, n to the 0.01 size independent. Okay. Turns out that even this is difficult for this problem. So this is one of these really, really difficult problems. In fact, you can prove that if this happens, then P equals NP. Okay, so if you can have an algorithm like this, then P equals NP. Okay, so we'll see this a little bit in the last one or two lectures. Maybe not last one or two, actually, maybe a couple of weeks from now. It's almost last. Okay. All right. So this is a hard problem. Okay. But of course, you can always ask, what happens if you try to do this framework that we've been doing? Because it turns out that writing optimization formulation of this is very simple. In fact, it will be very similar to the formulation we had we saw for vertex cover. Right? Because if you think about it, vertex cover is just saying you want to pick so one is a maximization problem, one is a minimization problem. And in vertex cover that we just saw, you wanted to pick as few vertices as possible, so that for every edge, one of the endpoints was chosen. Now you want to add as many vertices as possible. Okay. So that you don't have stuff like this. So that no two endpoints of the same edge are picked. So, alright, so you can define the variables the same way. Okay, so xi's are 0, 1 variables. What would be the constraint that you would write? Like this, going by this thing, that for any edge you must less than equal to 1. Yeah, so you want at most one of them to be picked, right? So for all edges ij, xi plus xj is less than equal to 1. Because at most one of these two must be picked. Right? So you can't have both of them being picked. And so it turns out that as far as if you just phrase this as an optimization problem with discrete variables, xi being 0 or 1, then this actually captures this problem exactly. Because if you find any 0-1 solution that satisfies this, the ones have to form an independent set. Okay? Because you can't have two of them having a metric value. Because xi plus xj would be 2 for that. So this is actually a valid optimization formula. But now suppose you relax this. Right? So if you relax to now consider this problem of maximize sum over ixi subject to for all edges ij xi plus xj less than 1 and 0 less than xi. So I want to claim that this relaxed problem, where you converted the binary variables to continuous variables, is totally meaningless. Okay, and the example that I would like to give is, suppose you have a graph that is a key. So you have n vertices such that every pair is connected. So I mean, I do too many vertices. So every pair is connected. So this is a key of size 5. And in general, I think suppose that there are n vertices like this. So what is the size of the maximum independent set in this graph? Like how many vertices can you choose so that among the chosen vertices there are no edges? So you think 0, but it's actually 1 because there's no self loop, so you can always choose 1. But that's not us, right? Yeah, so you can't choose any non-trivial set. So the optimum for this independent set problem, this is equal to 1 for this guy. Now, I want to claim that the solution with a pretty large value here. Can you guys think of the solution? Like again, inspired by the previous slide. Yeah.
That's before we put half on every.
Yeah, so you just put xi equals half for everybody. Okay, all xi equals half. And this is perfectly valid. This is a perfectly valid solution because xi lies between 1 and 1, and xi plus xj is less than equal to 1 for every I and j. Okay. But note that this is a totally meaningless solution, right? And this has a total cost of this has a value of n by 2. Everybody is half, so sum for n xi is n. So sometimes these kind of relaxed linear programs can be completely useless. Okay, like in this case, this doesn't tell you anything about the independent set on the graph. So, alright, so this is so of LP equals n. Okay, so let's just quickly summarize. Okay, so what we've seen are 3 examples so far. Okay, so one we saw last time is matching, where you get lucky and all corners are actually integral. Okay, so in this case, you can actually solve the discrete optimization problem by solving this continuous problem. And the second example we saw, we said that the corners are somewhat integral, and this led to an approximation algorithm, where we said that you can do some rounding and you get some factor 2 approximation. And the third example we saw for independent set, we said the corners can be totally used. So in practice, it will often happen that the first linear program you write for a problem will probably be totally used. Okay, and often what people do is you add some constraints. Okay, so you won't see examples of this, but there are a lot of problems for which you think a little bit more, maybe you come with a different formulation, and that turns out to be useful. So this happens in many problems. Okay. Not for independent set though, because independent set, as I said, is a very difficult problem, and we don't have any good way of solving it. But it happens for many other problems like scaling problems and so on. Okay, so clustering. These are problems where if you write down the obvious formulation, it will not be any good. But if you think a little bit more, write some better constraints, you end up with something that gives an approximation. So this is the quick summary of things we've seen so far. So any thoughts, comments on this? Okay. So I wanted to give a sense of another whole idea, which is this is another common idea that people use. So when we saw this rounding over here, right? So the rounding procedure here, this was a very basic rounding, right? So if xi was less than half, it's something. Xi was more than half, you come up with you round it up to 1. So often it turns out that something more probabilistic can be done. Okay, so this is something that you guys might have thought when I asked how do you round a fractional value to an integer value. Right? You could always, if you get a fractional value of 0.25, you could say that with probability 0.25 I'll round it up to 1, and otherwise I'll keep it as 0. So this is another natural way you could think of for rounding. Okay, so and it turns out that for some problems this actually works much better. Okay, so there will be no such clean threshold that you can come up with, but you can actually round things probabilistically and get a decent solution in expectation. Okay, so we'll see an example of this, and I won't be going the full details because I don't think it adds too much intuition, but I'll give you the outline. Okay, so this is, so we consider this hiring problem. I don't know if you guys remember, not expected to remember, but we saw this in greedy when we were doing greedy hiring. Okay, so where you have n people, each person has expertise, and you have m different skills, and each person has expertise on a subset of these skills, and you want to hire k people so as to maximize the total number of distinct skills. So you want to cover as many different skills as possible, and you have a budget of k. So this is so this is a problem for which we saw, I think, when we were doing greedy algorithms, you always pick the person who's giving you the most relative advantage. Okay, so we'll get a very similar round using a linear program. And this here, as you will see, the analysis is much more just pure algebra. Okay, so if you know how to just do the algebra, you just get the same approximation without any like clever reasoning. So if you remember there, we had to do some clever reasoning about why this solution is at least like 0.63 times off. Okay, so here you just get it by some straightforward manipulation. Alright, so let's see that. So you have n people and you have m skills. And your goal is and here's something like this. Your goal is to pick k of these n so that you maximize the number of decisions. Right, so yeah, so I thought this would be a good exercise for you to write down the data program as well, because it's not clear how you would write an optimization formulation. So how would you write an optimization formulation? So it's clear what one set of variables is. You want to select a subset of the people. You better have some variables for people. But how do you have? Okay, so one choice to say that, okay, so you have xi is xi, one for each choice. And these are supposed to be 0 and 1. This is in the original, yeah, we are writing the discrete formulation. So these are supposed to be 0, 1. We know that you've got to select k of them. So we know that sum over I is I equals. So now what is the objective though? So the objective is tricky capture using these variables, at least I think. So how would you decide if I mean in some sense you want to maximize the total number of distinct skills. So sometimes you want to say, is a skill captured by the excels that you've chosen or not? You need a variable. I mean, you need some. I mean, it's better to have an answer. But, so how would you capture this?
these two people.
Note that you don't have to have one person of each skill, right? Because that's the objective. I think you're trying to say that, in some sense you want to cover all the skills. But we don't want to cover all the skills. We want to cover as many as possible, right? So somehow that should go into the objective. Right? So what is the clean way of, actually if I just gave you these variables, xi's, which are zeros or ones, and I ask you, is skill J captured, right? In the sense that is there an expert on skill J? How would you do this if somebody just gave you X? This is an easier problem.
Every person is set will see if they have edge to skill check.
Okay.
If you find some person, you cover the skill of this.
Yeah, so what he's saying is that you look at skill J and you look at all the people who have skill J. Okay. And these are just the neighbors of this vertex J. And if the xi happens to be 1 for even one of them, then you are in good shape. If xi is 0 for all of them, then the skill has not been covered. Okay, so is this clear? So you could always say that look at skill J, look at all the people who have an edge to this J, right? And if xi equals 1 for even one of these people, then you're done. So in some sense, so can you write? So how would you make this a little bit more formal, right? Like how do you write it abstractly? Right? Or you want an objective at the end of the day. So let me write down observation. Skill J is okay. So this is the observation side. So it turns out, okay, let me give you a hint. Okay, so if you don't know, what to do, you try to introduce some more variables. Okay, so let's say I want to introduce a variable, which I will call z sub j. So z sub j is supposed to be a Boolean thing. It's supposed to a Boolean variable that is 0 if skill my writing is bad. Okay, so you have.
So instead of like using z of j, I could probably have like y of ij, which indicates if I has the skill j, and if I do a double summation over yij into xi, so summation over yij would be greater than 0 if that skill is covered. So I could like simply do, or if I use zi, I could do a summation over zj into x of I.
So yeah, so I think what you are saying is, in some sense, I look at so your yij's are basically 0, 1. Right there, a person person I has a skill j, or he or she doesn't. Right. So your y's are just 0, 1. So in some sense, you're saying that skill j is covered. What you're saying is, in some sense, a mathematical representation of that observation is if and only if sum over all I that are neighbors of j in this graph. Note that you are a neighbor only if, like I is a neighbor of j only if I has the skill. Sum over the neighbors of xi is bigger than or equal to 1. Okay, so that could be an alternate way of writing down exactly what you said. Okay, so is this clear? So skill j is covered if and only if this is true. Okay. And if you had 0, 1 variables, right, you could even have taken this one step further and said that skill j is covered, or z sub j, I want to claim, is exactly equal to min of 1 and sum over I in neighbors of j x sub. Okay. So this is something I want to claim. Okay, so and right. So because this skill j is covered is like saying zj is 1. Right? So zj is 1 if and only if the sum is more than 1. Otherwise, zj is 0. Okay. So and the sum is an integer. So if the sum is not bigger than or equal to 1, it's equal to 0. Okay. So in other words, you can always write zj as min of these things. And this gives you a way to write a linear program. You just say that you introduce these new variables zj, okay? And now you say that 0 less than or equal to zj less than or equal to 1. And zj is also additionally less than or equal to sum over of x. Okay? If you have a min of two things, it's easy to write as a linear equation. Right? You can say that it's less than or equal to this and less than or equal to that. And you make this a variable. And this is how you would write this as an optimization problem. So in fact, you could have avoided writing as you could have avoided introducing a new variable by just saying I want to minimize the sum of these quantities. You could have said that, but we are just introducing a new variable to make notation convenient. Okay, so your goal is objective function is now to maximize sum over j, because zj represents if skill j was covered or not. You want to maximize the number of skills that were covered. So you just sum over all. This gives you the number of skills that are covered by the current solution. You maximize them. Alright, so I'll pause a little bit here because this is one example where actually probably after these paths and stuff, this is one example of a simple problem where writing a formulation is actually not obvious. Okay, but this kind of a min trick is something that shows up often. Okay, so that's why it's good to see this. Yeah.
You saying that you don't need to introduce another variable cj,
Yeah.
and instead you could minimize the sum over x's. How is that?
Yeah, so you can write an optimization problem I mean, as long as you don't require it to be a linear optimization problem, right? You can always say that my variables are the xi's as before, and xi belong to 0, 1, and your constraint is simply sum over I xi equals 1, sorry, equals k, and your objective can be maximize sum over all j of min of 1 and sum over I inverse of k x. You could just have put the whole thing in the objective, right? So now you don't have to define any new variable because it's min of these two terms, and we know that if this min is 1, then it's covered. And if this min is 0, then there is nobody who covers skill G. So you could have written it like this, but now it becomes tricky to write this as a linear program afterwards because you have this weird min. Okay, so the trick to getting around it is to introduce a new variable called Zj and basically writing the constraint.
And how is Zj a continuous function?
Yeah, so ideally you would want Zj to be min of these two, okay? And the min of these two, you just say that it's less than equal to this and it's less than equal to this. And these are arbitrary real numbers now. So once you relax so that it becomes, so that x's are fractions.
Now these are not zeros and ones. Is that what you're saying?
Yeah, in the current formula, in like an integer formulation, a discrete formulation, these are only zeros and ones. Okay, but now the moment you remove the restriction on x's, right? Because we will eventually say that like this would be the discrete optimization problem. We will eventually remove this restriction on the x's and change it to 0 less than equal to x less than 1. Okay, so this is the process that we call relaxing. Okay, so.
But then over here, like, what would be the physical significance of this thing when you change x size to continuous range?
Right, so this is what we've been trying to say, right? Like in some sense, you want to solve this discrete optimization where if you think of the feasible space, they are just a bunch of discrete points, and you want to find one of them that has the largest objective value. Instead, we are saying we are moving to this kind. Yeah, so let me draw a picture. So this often helps. So we often have this bunch of discrete solutions. You want to find one of them. Usually there are exponentially many. You want to find one of them that has the best value of subjective. But instead, what you do is, in all of these things, you find a continuous object that kind of has all of these things, and you optimize over this object. Okay, and you find the point in this bigger object that has the best objective value. Okay, and this could be a point, and what we've been seeing is that this could be a point that is not one of your original 0-1 solutions. Okay, this could be some fractional thing. Okay, and yeah, so geometrically, this is what is going on in this relaxed and non-parallel. Okay, so you get some point that is here, and then such a fractional point, you round it to one of these integer things. Okay, and that's what we would like to do. So yeah, geometrically, this is one way of seeing it. Okay, so right, and in this case, introducing a new variable is actually, it's an interesting thing. It's like enlarging the dimension of the space. Think of now having like a third coordinate where those correspond to the z's. Okay, and yeah, then it becomes more complicated to visualize. That's why it's kind of hiding it under the rug. Okay, so introducing new variables is like introducing new dimensions. So, yeah. Alright. So, okay, so this is the formulation. And you introduce these new variables. So, okay. So let me just give reason as to why this also does not exactly capture the solution we want. Like you can have, and this is, so suppose you have 3 people. This is actually inspired by the same triangle example. Okay, so it's, if you think about it, it's the same thing. But yeah, if you have 3 people, and if you have 2 people with 1 skill, 2 people with 1 skill. So these are people, these are skills. Okay, so person A, B, C, skills 1, 2, 3. A has skills 1 and 2, B has 1 and 3, C has 2 and 3. Now, if I this is probably not a great example. So I thought it was saying half, but then your K would be 3 half. So let me come up with a better example. So I want to duplicate this, I guess. So let's say you have 2 triangles. Okay, so two of these things. It would be tricky for me to draw the same. So this is D, F, and these are 4. And I tell you that K equals 3. So if I tell you K equals 3, now one candidate solution for me is I can get X equals half for everybody. Okay, and this would mean so if we looked at for any skill for any of the skills, so you have 2 people, therefore the sum of XA plus XB is 1. Okay, so the min of the sum of the neighbors comma 1 is always 1. Okay, so you would conclude that there is one person who has I mean, at least if you went with this fractional solution, for every skill, there's a total of one person who has this skill, right? So this is kind of a cheating solution, right? It's like saying, yeah, you have fractional people and they happen to cover this thing, right? So you can conclude that, yeah. So this is a bad solution. So all. Okay, but if you look at the actual optimum, if you are only allowed to pick 3, then you can see that maybe you can pick all of them in the first one. You can only pick 5 of the 6 skills. You can't cover all the 6 skills. So yeah, so you have these kind of bad instances where like integer. So yeah, so any questions on this example? So yeah, one thing to remember is that unless you are very lucky, as I stated before, all your corners will not be integers. Okay, so you will actually end up finding a fractional solution that's probably better or strictly lower value or strictly better value than the best integer optimum solution, but you somehow need to massage this to come up with an integer solution. So yeah, this is another example of this. Integer opt is only 5, but opt of LP is 6. So the LP thinks you can cover everybody, but the actual solution you can only cover 5. If you're allowed to keep only 3 people. All right. So this is one example, and I wanted to say that this is an example though in which like rounding at a threshold turns out to not really work. Okay, so this is unfortunately this is a little tricky to see, but I mean I guess yeah. If I remember correctly, there is one homework problem that deals with something very similar. Okay, so you will you'll do something like this. But this is also an example where probabilistic rounding actually works. Okay, so thresholds don't really work, but if you do things probabilistically, so I wrote down the analysis because this is a little bit of a, I mean, yeah. So I thought, hope there are no typos here because I can just share the slides and you should be able to see this analysis because doing the analysis takes a bit more time. So I'll just outline it very roughly. Okay. So what I want to say is that the obvious probabilistic rounding, where you choose a person I with probability xi. Okay, so you solve the linear program that we wrote down. Okay, so these constraints like zj is equal to this, maximize on stuff gives you a linear program. Okay. And now you solve this linear program. You got some fractional values x's and z's, and I want to round this, and I want to round this by saying that you choose a person I with probability equal to xi. Okay, so this is like saying set yi equals 1 with probability xi, or actually since I'm calling it capital X. Yeah, let capital Xi be 1 with probability small xi and 0 otherwise. Now, yeah, so you can now define a random variable, right? Because this is a probabilistic process. So capital Xi, let's say, is the random variable, that is 1 if I is chosen. And this is what you, okay, so I should have used Z here because Z is what we've been using, capital Z is what we've been using. But anyway, never mind. So how do we analyze this procedure? Right? So we're just saying, you take this very simple procedure, you have these fractional solutions, round each one up with probability equal to its value. So if some x is 0.1, it has a very low chance of being rounded up to 1. Whereas if an x is like 0.9, it would have a pretty good chance of being rounded up to 1. So this makes intuitive sense, right? Like you would want to do rounding like this. So I don't see agreement here. So any thoughts about this? Because I mean somehow a higher value means that you may want to round it up to 1. That's because you're not. Remember, in this whole thing, the game is you want to start with a fractional solution, end up with an integer solution that's not too different in cost. Okay? So if you don't want too much change in the cost, you'd better have your integer solution being close to your fractional solution. Okay, so this is why these kind of randomized things work, because you round up only if you are close to 1. If you are close to 0, very unlikely that you will round. But anyway, so yeah, you can do this, and it turns out that this quantity you should be able to see immediately. Okay, so if you round like this, the expected number of people you actually pick would be exactly equal to sum over ixi, which is equal to k. This is just by linearity of expectation, okay, because you want to see how many of the caplexes are equal to 1. And the expectation of the sum of caplexi is the sum of the expectations, which is equal to 2. And a more complicated analysis, a slightly more, I mean, it's not very difficult, but you can just write this down. It shows that if you do this process, then you can relate the probability that a skill is covered, okay, to a quantity that depends on this, okay, the sum over I, who are the neighbors of these xi's. Intuitively, this is believable because if you had a bunch of xi's that were all half, let's say, and these were all connected to this one vertex. Now, it's pretty unlikely that none of these guys is picked. Okay? So you can relate the probability that the skill is covered in some sense to this. Okay? And if you just do some basic algebra, you end up getting the same approximation bound. So yeah, so the point here is not quite to understand this analysis in detail, but to see that this very simple probabilistic procedure of rounding up a value with probability equal to this xi actually works, and you can analyze this. Okay. So yeah, so let's stop here. So this ends up giving a different way to obtain this algorithm for discovering problem. Okay, so last time we had to do some more clever analysis to do this. This is just some basic algebra case.